Grams.
Feel free to cut me off.
Okay, so today we're going to talk about shear and moment diagrams. And before you draw a shear and moment diagram, it's important to understand the general concept of internal forces inside of, in this case, a beam. Beams are what we're interested in. So you could potentially have an axial force. You could have a beam that has compression or tension. For example, when we make bridges, sometimes we will make them what we call pre-stressed. So we put some compression into them ahead of time to help strengthen them when they carry these transverse loads. So there could be axial force, and that axial force causes a normal stress. We're saying that our x direction is our longitudinal direction, or the length of our beam. Typically, we always use x for the length of our beam. Then we will have some moment acting on our beam. If we have any transverse loads, those will typically cause moment. And so if we have moment, we haven't gone through the derivation yet, but you will see in future lectures that that moment also causes normal stress in the beam. And we have shear that exists in the beam because of these transverse loads. What do I mean by transverse? Perpendicular to the length of the beam. Okay, so which is typically how we load a beam. So transverse loads also cause shear. Now that shear stress will cause, or sorry, that shear force will cause shear stress. And once again, I haven't shown you yet that relationship between the two, but after we get through moment, we'll then go to shear in beams, and you'll see that there's an equation that relates the shear force to the distribution of shear stress, and it's in two directions, of course, because anytime we have a shear stress component, say tau xy, we must also have a tau yx. And then depending on how you load this beam, you could also have an xz. So we could have our xy, we could have an xz, depending on the direction of the forces being applied. All right, so we're designing our beams for these maximum values of V, M, and P, where P is the axial force. And in order to determine them, of course, you draw a free body diagram. You have your beam, you take a section cut, and then you draw the free body diagram for that section cut. The whole beam together helps you get your reactions if it's determinate, but then once you have your reactions, you can then take a section cut. So you have, say, your beam with some loading, and you can get these reactions. And then once you have those, you can take a section cut. You have this loading, and now you know there's got to be some other kind of reaction here, or not reaction, but internal force. That would be your shear force. And conceivably, you could have a P or an M, depending on how this is loaded. So those are your three options for the internal forces that you could have, and you solve for those using equilibrium. When you take a section cut, so for example, if you take and you cut it apart like so, you're always going to have equal and opposite. I guess I should draw those the other way. You're always going to have equal and opposite stresses on each, or forces on each. So if you have shear going in one direction on the left side of the cut, it's going to be going in the other direction on the right side. Same thing with moments and axial loads. This next point is extremely important. It may seem obvious, but it's a very common mistake, that if you have distributed loads, you can replace them with a concentrated load, but only the amount of that load that's acting on the segment that you've cut. So for example, if we have this distributed load all the way across the beam, that can be replaced. Let's see. Okay. There we go. That can be replaced with a resultant like this if you're doing equilibrium of the whole thing. But if you are doing equilibrium of, say, half of that member, you have your distributed load. Now when you replace that with a equivalent force, it has to only be the force that's equivalent to the load on this segment, and you place it at the centroid of that load. If you were to take, say, this load here, which, let's make that a different color. So if we were to say take the whole load and turn it into a resultant at the center, and then say this cut is at the center, you would have it placed there. And as you can see, that green and that blue arrow are going to give you two different answers, especially in terms of your moment. So it's extremely important that you only replace the portion that represents the segment that still exists after you draw the part of it. So, because even the worst case would be if you took this cut slightly to the left of that middle, you wouldn't have a force acting on it at all if you had done it improperly and represented it as the resultant of the whole force. Sign convention is really important. If you have a sign convention that differs from what I'm about to show you and it works for you, that's fine. But this is what this textbook uses, and so that's what I'm going to use. So for our distributed loads, if this is our beam, positive distributed load is upward. And for tension, this one I don't think I've ever seen different. This one's always outward. The distributed load I've seen the other way. In fact, I like to do it the other way, but this is the way the textbook does it, is up, tension is out. Shear force is clockwise rotation. So if you have a cut and you're looking at the right-hand side of a cut, or let's see, if your arrow is to the right of the member, it should be pointed downward. If it's to the left of the member, it should be pointed upward. That would give you clockwise rotation. And my favorite, positive bending moment always makes the beam smile. So one way to get our values that we're interested in is to use an arbitrary X location to determine our internal force. So what I mean by that is if I have, say, a beam that looks like this, I would break this up into two regions. I'd have the first region and then the second region. And starting here, I would have X going from 0 to whatever this L1 is. And then it's your choice. You can either have X go all the way to the end, or you could restart X again here and then get your equations accordingly. You just have to be careful because when you're getting equations for shear and for moment, how you define X will change your equations. The end result is going to be the same, but for example, if your shear diagram, for whatever reason, we're going to look, let's say it was going to look like this. If you define X as starting at that point, this is going to be a linear equation of the form mx. Right? You have a slope and then an x value. Whereas if you were defining X as being continuous from the left-hand support all the way across, now you need to track that all the way back to where it would intersect X is 0. So now this equation is going to be an mx plus b, and you need to figure out what that b would be at this initial X equals 0 location. So my personal favorite is to restart X at any point that I know the equation will be changing. So really at any time I have my supports or a change in load or whatever. But then I know that when I graph it, I have to keep that in consideration. And when I piece all my pieces together, it has to make sense with where I've defined X. Okay, so this part should be straightforward. Take the sum of the moments equal to 0 to get the bending moment at a point. So you take the sum of the moment at the point that you took your section cut. So this is our beam. The sum of the moment about that point will give you this internal moment. The sum of the forces that are parallel to the member will give you your tension, and the sum of the forces that are perpendicular to your member will give you your shear. And then you plot those as functions of x. Okay. And if you take this arbitrary x value, so instead of, so say L1 is 8 feet. Instead of say cutting at 4 feet or 6 feet or 2 feet, I cut at what I call x. And as long as there aren't any concentrated forces, point loads, or supports, I know that that same equation is going to govern the whole region. And so I can set up my length in terms of x, and then all my equations, when I solve for the moment or the shear, end up being functions of x. Any questions so far? Excellent. Okay. So that's one way to solve for your internal forces. That's kind of a formulaic method that doesn't require a lot of intuition, but has kind of defined mathematical procedures. My preferred method, because it's faster, is more of an intuitive method, where you strategically determine certain values at certain locations, things you know to be true. For example, certain supports have zero moment or have a known value of shear. So I like to identify those points and then use what I know about the relationship between my load and my shear and moment to visually draw what it would look like, and then I can calculate the numbers using some basic geometry, basically. Cool. So the things that I know. When I have a free support, so say I have a cantilever, out here on this end, I have zero shear and I have zero moment. So whatever my diagram looks like, I know it has to end at zero for both shear and moment. When I have a pin, let's say I have something like this, and when I say pin, that includes rollers as well. So when I have a pin or a roller, I know that the shear, you gotta be careful with how I say this. On the left-hand side of the diagram, the shear is equal to the reaction. And at any other point, I know that there's a change in the shear that's equal to my reaction. And I know that the moment is zero at that point. So whatever this reaction is here on the left-hand side, I know my shear diagram will start at that value, and then I know it's going to end back at zero. It always ends at zero. No. Unless there's some shear moment at that point. But it always closes. Okay. And I know that the moment at these 2 points will also be zero. The reason that you get moment is because you have resistance to bending at that point. But if you're connected to a hinge that can rotate freely, there is no resistance to moment. Therefore, you can't develop moment. The way that you develop, if you fix it and you don't let it rotate, now you have a moment present. So at a fixed end, what I know to be true is that if I have some reaction here, that will be, assuming it's on the left-hand side, that will be the value of my shear, and that will be the value of my moment, whatever that reaction is. You do have to be a little bit careful with the sign. Sometimes you can get turned around with the sign, but there are tricks for that as well. All right, so then we look at our loading. If I have a region of no loading, I know that my shear diagram is constant. So if I have, say, just a point load here in the middle, I would say this to the left and to the right of that point load is what I call no loading. So the shear diagram for that should be constant. I already know, or let me ask you, what do you know about the shear at this left-hand support?
It's equal to the reaction.
It's equal to my reaction, which happens to be half of that load. Then I move to the right and I say, okay, now I have no loading. That means there's no change. I have a constant value of shear. So that's step number one. Step number two is point loads. Anytime I have a point load, my shear moves in the direction of that point load. So this point load is pointed down, my shear goes down by that same magnitude. And then what happens when I continue to the right? Continues constant. And then at the end, I have a reaction going up and it closes my diagram. Always has to close. So I can just look at this and I intuitively know what shape it has to take. I didn't have to do any algebraic formulas. And then I can come in and I can say, well, if I want to know this magnitude here, I need to solve for the reaction. And there we go. So if we want to know the moment, we know that moment is linear anytime we don't have an applied load. So that means that, well, let me back up. First, I know that my moment has to be 0 at these two supports. And then I know it's linear anytime that I don't have any loading occurring. So it's going to be linear here, and it's going to be linear here. So then the question is, what happens at that point? As you all know, it just comes together like this. But what's really happening is it's continuous with a sudden change in slope. So anytime you have a point load, there's no discontinuity, so I don't jump to a different value, but I do have a sudden change in slope. So it creates this triangle thing. All right. So next step is our uniformly distributed load. And let's see. And linear load. So we'll put, say, a uniform load and then a linear load. We know we're going to start with some reaction. For our shear. And then we're going to have, if we have a uniform distributed load, you will always have a linear shear diagram. So this is going to go up. And if you have a linear distributed load, which is this right here, so it's increasing magnitude, it is going to be quadratic. So the scale that I've chosen is going to make that intersect with the other diagram, but let's see if we can. So it's going to go like that. Oh, I don't know what I'm doing. Don't do that. That was linear. Quadratic. No, I'm going the wrong direction. Should be going down. Right, they need to go the same direction as the loading. So if I have distributed loading going downward, this linear slope needs to be going downward. Then this continues downward. That's better. That's better. And now my reaction on the other side, which will be larger because more of the load is over on that side, is going to come back up to close it. So I don't have any numbers, but I know the general shape. And so when I have that uniform loading, it's linear with no discontinuities. And when I have the linearly increasing or decreasing distributed load, it's quadratic, but once again with no discontinuities. So at this point right here, it should be continuous. There should be no discontinuities. And in fact, it shouldn't have like a sudden kink in it because these two have the same magnitude at this point. It should just be gradually changing from there. Yeah.
Do you know, is there an easy way to determine if the bending moment part of it should be concave or convex?
Yes, and we will talk about that. Okay. Yeah, that's one of the, when it comes to quadratic diagrams, that's the hardest part. Okay. Okay, so then for the moment, let's see, moment. Come down here. We know we start and we end at 0. For the uniform distributed load, it's going to be quadratic and continuous with a gradual change in slope. So let's see, we're going to be quadratic. So to answer your question about how to know which direction it goes, let's see, do I have it written here somewhere? I don't guess I wrote it. Okay. What we're going to talk about in just a second is that the slope of the shear diagram is equal to the distributed load. So this slope here is equal to that magnitude. So if this has a positive magnitude, this should have a positive slope, and vice versa. So similar, your quadratic equation, so if we're integrating this linear portion, that should have, so your moment should then have, the slope of your moment should be equal to your shear. So where we have this intersection here, we should have 0 moment. And where we have this positive value of shear, we should have a positive slope. But the problem is that could go like this, or it could go like that. So the other thing to keep in mind is what I just said is the slope of this diagram is the magnitude of the shear. So yes, we've agreed that it's positive this whole length, but it starts from a relatively big positive number and goes to a relatively small positive number. So that means that your slope should be starting with a relatively big positive number and then approaching 0. So the other thing to think about is you rarely have, there are cases, but typically unless there's like an applied moment or something, you don't typically have these sudden discontinuities. Typically, so for example, if you have this continuous equation here for your shear, you should have a continuous equation for your moment, which would mean that this one doesn't make a whole lot of sense because it needs to be able to continue down like this. So now the whole rest of this has a negative value for the shear, so it's going to have a negative slope for this, and so you'll come across like that. And then it gets really hard when you get down to linear distributed loads because now you're trying to draw a cubic, but you're only drawing a very small portion of a cubic. It's never going to look like this. It's just going to be, say, like that portion of a cubic, which looks very much like a parabola. So don't worry about being too exact with those, but what you do want to do is it should still have the same general characteristics. So it should be getting more and more steep as you go down because the slope is, once again, is the magnitude of this shear. So if that magnitude continues to be decreasing, it needs to be getting more, I don't know, my scale's off. Something, this is really terrible. Make it like something like that. And what you'll notice is that there shouldn't be a discontinuity. So once again here, you should just have a continuous with a gradual change in slope. You shouldn't have a kink in it.
So since the moment's quadratic for the shear diagram, the moment diagram, it'll be for the second part. It'll be
Cubic?
Yeah, cubic, right?
Yeah. So what I typically do, okay, I'm sorry, go ahead with your question.
Would it like ever like do this, go back down, go back up on me?
No, because it always has to have a negative slope because this whole thing over here is negative.
Okay.
So like I said, you're just taking a very small portion of a cubic. And so what I typically do is I draw it looking kind of like a parabola, and then I put a little arrow here that says cubic.
Okay.
All right, so then the last point is you might have an applied moment. Are you coming back? Is he coming back? One of the teams is going to be down. No, he left his stuff. He's coming back. Oh, just drop everything and run. Just go. Okay. Okay, so you might have a beam where we're applying a moment at some point within that beam. So when you come to drawing your shear diagram, it actually has no effect on your shear diagram. So with the exception that there are going to be reactions because of this moment. So let's see, so your reactions are gonna have to go the other way. So it's going to be like this. So your shear diagram is only based on these reactions, which means your shear diagram would go up, over, and then down. Right? Does that look good? I'm waiting for a decision.
Yeah, no,
Okay. But this applied moment in the middle has no effect on that shear diagram. You don't have any change in slope, any change in magnitude at all. Then it does create a discontinuity in your moment diagram. So just like a point load causes a sudden jump in the magnitude of your shear, this causes a sudden jump in the magnitude of your moment. So if you have your diagram like this and you start at 0, so you're going to be going up, and then you have this sudden jump, and then you're going to go up again. And you might say to yourself, well, self, how do I know whether this is jumping up or jumping down? Well, 2 ways you know that. One is when you're integrating the shear, it's positive. This whole thing is positive. So these lines always have to be positive slope. You know you start at 0 and you end at 0. So you know those 2 lines have to look like that. And therefore, you have to have this go down in order to make it continuous. So you always start with the things you know with certainty, and then you fill the rest in. But there's another way. There's another way to figure it out. I always think about what would that moment be doing to the portion of the beam that is to the right of the moment? Because here's the problem. If you look at the left-hand side, you might think, self, this looks like a happy beam, right? This looks like a positive moment. But don't be deceived. You always look to the right of what the moment is doing. So you keep this moment rotating another 180 degrees, right? The same moment. It's actually making the right-hand side very sad. So as you're moving from the left to the right, it's making the beam sad. So therefore, it's going down. That's what happens in my head when I do moment diagrams. Okay. Compute shear just to the, so anytime you have a point load or a reaction or a concentrated moment, you can compute the values just to the left or the right of that to get the value of these diagrams. You can probably get the shape in a minute, and then you spend the rest of your time going back and taking those little cuts to figure out what these corresponding important values are. And so I say just to the left and the right of point loads or reactions, or at the beginning and end of a distributed load. And then compute moment at points where point loads or reactions are applied. Okay, basically the same thing. It must always close. It must always end back at 0, start at 0, end at 0. Okay, one last page. Okay. So we have these relationships between the distributed load, and we've already kind of alluded to them in order to finish our to finish talking about that table. But it's the idea that if we have a small segment of a beam and it's being acted on by some positive distributed load, W, and this is acting over delta X, and let's draw our shear as being positive. So that's shear at X, or let's see, we'll call that the shear, and then this is going to be shear plus delta shear. So there's a slight change in the shear from the left to the right-hand side of this segment, and so the right-hand side becomes V plus delta V. So if we do equilibrium, sum of the forces in the y direction, we're going to get this equation here, where we have positive V on this left-hand side, negative V plus delta V on the right-hand side, and then positive W multiplied by delta X in the middle. So the 2 V's, those cancel out. You're left with delta V equals W delta X. We can divide by that delta X, and we can make delta X very, very small, which says that the rate of change of your shear, rate of change is also known as, thank you, slope. So the rate of change of your shear, or the slope of your shear diagram, has to be equal to your distributed load. And remember, if distributed load is going up, that's positive. So that means the slope of your shear diagram is positive. And then if you want to know that slope, you want to know the actual magnitude of it, all you need is to look at your loading that's been given, assuming it's constant. So now if your loading is some function, you can integrate it. So we can go back to where we have dx on the other side. So we can say that, dv equals w dx, and then we can integrate both sides to get that the shear is the integral of that w. So if, like I said, if the loading is some function, you could integrate it to get the function of your shear. Important point is when you do this integral, what you're really doing is you're integrating between 2 points. So you're actually getting the change in shear. It's okay to write it like this if you're getting an equation. If you have an equation of your shear and you're integrating that equation, but just always keep in mind there's some starting value, there's some constant that needs to be added to it, right? So if I integrate, I don't want to integrate. Yeah, if I integrate 5, God, what am I thinking? It's embarrassing. But you get a constant. So if you integrate 5, it's 5x plus c, right? Okay, good. Like, you often leave that c off. You often don't care about it. But if you're going to be exactly plotting these equations, you're going to need to know what that c is. Oftentimes, you already know that you're starting at a value of 0, or if you're going across this diagram, say you have a line here, and then you're going to have another line here with a different slope, you already maybe figured out the starting point. So you're not so concerned about what that constant is. But if you need to know, or if you're calculating the change in shear, then, no, let me take it back. If you're calculating the change in shear, then that constant doesn't matter because it subtracts out. So it only matters if you want to know where that starting point is of that line segment. Okay, so if you integrate w with respect to x, you get this change in shear. We can do the same thing now going from shear to moment. So we can take a little segment of a beam that is experiencing positive moment. Make sure I draw this picture for you properly. Okay, so we have W going upward. We have moment on the left, moment plus delta moment on the right, shear forces. So you can imagine that there were moments on this first diagram, but they didn't matter because I took the sum of the forces. Moments don't enter into that equation. But now I want to take the sum of the moments. So I have a positive moment coming from this m plus delta m. I have a negative moment coming from the m on the left. And let's see, we have our shear and our shear plus delta shear. So I have, where did I label part B? We have to pick, for the moments, it doesn't matter what point we're taking the moment about. They're always the same in every equation. But if I want to start getting moments of these forces, I need to pick a point to take the moment about. So I'm just going to pick this point here. I want to put that in blue. So I'm going to call that D and take the moment about that point, which means that this force doesn't apply. But I do have, if this is delta X, I do have a negative moment caused by the shear force on the left. And then I have should also be negative, shouldn't it? The moment caused by the distributed load. So this should probably be a negative sign. Okay. All right, so these two cancel out, this moment and that moment. We're pretty confident that this should be negative, yeah? Okay, that means it should be positive here, because I'm moving that to the other side of the equation. Okay, good. Okay, eventually this has to get out of my problem because I know my end result's fine. Okay, so at this point, I'm gonna say this part is essentially 0. When I take delta x and I take the limit of it going to 0, the square of delta x is even smaller. So that term now goes away. Now it no longer matters whether it was positive or negative. But I'm left with delta m or dm equals v dx. So I can divide by dx once again, and I get that the slope of the moment or the rate of change of the moment is equal to the shear. And same thing, instead we could integrate the shear with respect to x to get our moment. So that's why when you go from your shear diagram to your moment diagram, to get the magnitudes of the moment, you can just calculate the areas under the shear diagram because those areas are equal to the integral. And so what you're getting when you take those areas is the change. When you leave off that constant and you just say if you have a shear diagram that goes like this area under here, if this is A and this is B, that's the change in the moment from A to B. So that's how much you increase. And then down here would be how much you decrease now, because that's a negative value. So maximum moment occurs when the slope is equal to 0, right? If you have a moment diagram that goes like this, when the slope is equal to 0, that's your maximum. So when the slope is equal to 0, that means your magnitude of your shear equals 0. Compute the area of the shear diagram up to that point, and then that will give you your value of that maximum moment. Okay, explain, okay, so we talked about, do you want me to go over concavity again? One more time, and then we'll move on to March Madness. Oh my God, I can't wait. Okay, so what time is it? Okay, it's gonna be mad because we only have like 20 minutes for it. Okay. So once again, if we have, say, a distributed load, the shear diagram is going to go like that. So the question is, how do you know whether something, I think by intuition, or repetition, you know that this is the moment diagram, but how do you really know that? And how do you know that in another situation where it's not so apparent? So if you have a positive or a negative slope, that indicates whether you're concave down or concave up. So this slope here is negative slope, which means I get a negative parabola or concave down parabola. And then the magnitude of that parabola is, the slope of that parabola is always the magnitude of my shear diagram. So I'm starting with a high positive number. So that's my high positive number. I'm getting smaller and eventually approaching 0. So now my slope is getting smaller, which means that it has to be like this as opposed to like that. And eventually it approaches 0. And now it gradually gets more negative. So I have a small negative and eventually I have a big negative. Cool? All right, okay, you guys ready? Any questions?
Yeah, what are we doing?
Yeah. Okay, it's time for March Madness.